Hi, my name is p.f.webb from Cranfield University and I lead the Centre for Robotics and Assembly. We're a very keen and enthusiastic group of people who work on large-scale robotic assembly and manufacturing processes. Our real differentiator though is that we are very much tuned into the people side of manufacturing and robotics. Most of the work we do is collaborative.
So what we're interested in doing here is monitoring aspects of physical responses to technology, which might be indicative of how an individual's thoughts, behaviours and attitudes towards it, or emotional states, can be reflected. So if you think about it, your brain is an organ in the body that is it's very complicated, but it still needs oxygen, it needs water, it needs glucose to do what it does, and that has physical effects throughout the rest of your body that might give us clues to emotional states in particular.
I'm working on the Smart Cobotics project as the investigator, and I'm looking into find the smart ways to interact with the robots, how we can make sure that there is a human-robot collaboration working in a way that robot is adaptable to the human. It's like you are working in a playground and you want the robot to be your part. It's not like you are living in another world with the robot. So we want to make sure that the robots are the part where in the factory of the future, robots are the part playing an important part, and the operators are also playing an important part.
So this is the humanoid robot that we've got in the lab. We've had now for around four years, and in those 4 years he's been put to good use on our MSc robotics course. He's different to the other types of robots that we've got. So we've got many industrial robots, collaborative robots, but now is our sole humanoid robot. We can interact with now through his vision, so he will recognise a face, and then that will start the communication. Now, what is a humanoid robot?
A robot that is designed to look and act like a human.
Now, can you sit down?
Do you want me to sit?
Yes.
Okay, give me a second.
Within my team, 6 of the people have a human factors or psychology or social sciences background, which is unusual in a department full of engineers, but it helps to give a really exciting and vibrant atmosphere and fits very well with the ethos of the centre that we're working with the other partners on here in Smart Cobotics.
So what we're doing here as part of the setup in this particular study is we are monitoring aspects of brain metabolism. So we're looking at basically how hard your brain is working and using up oxygen as blood flows through it. We are looking at people's facial expressions to see if we can get clues to their emotional state. We also have some devices that are a bit like smartwatches that monitor skin electrical conductivity and your heart rate. And these can tell us things about, are you stressed? Is your heart beating faster? Are you using more physical effort? Are you frustrated? Are you happy? Are you in a relatively neutral mood? So one of the questions is, can we take this information and feed it back into the system that we're working on to make the system change its behaviour so that the operator can be safer or more productive?
So yeah, now it's been a really good tool for our students. We've had students using ChatGPT to kind of increase now's capacity and ability to learn and understand our inputs. And also he's met the Prime Minister and was in a fairly successful piece of social media content that's been viewed millions of times.
My own role within the overall centre is that I lead the package on, unsurprisingly, human factors and social impacts of using collaborative robotics. To me, if you don't get the people right, the robotics won't work. So that's basically what underpins all of our work. Also, if you look behind me, you'll notice that we do things at scale.
So here we took the opportunity of the off-the-shelf grippers, and this is flexible gripper as well. We can control the force of how much amount of force it can put while grabbing the object, and we have used it for basically picking up the hard metal objects as well as the soft material like apples.
Whenever we collect physiological data, it takes a lot of processing after you've actually collected it to do things with it to get it ready to be analysed. And if we can use machines to do this sort of laborious work, machine learning, deep learning or AI models to do it, it would dramatically speed up the way in which we generally go about doing our work, and it would be transferable well outside of these kind of contexts that we're working here with industrial robotics.
I always describe my research as building large wobbly things with robots. In other words, a lot of aircraft structures. But it soon became apparent with those type of structures that you can't do it all with robots and probably never will be able to. So you need to get people in the loop. And that brings all sorts of challenges and interesting problems.
So we are gathering this data. For this purpose, we needed and set up a use case. And to go ahead with that use case, we have set up this soldering cell, where in the soldering cell, we have the two robots working in collaboration with each other. So there's a robot-robot collaboration and a human-robot collaboration. Alright, so this is the soldering cell setup. This is the GUI for this setup, and this is a part of Smart Cobotics project, wherein the user inputs the points on the PCB, selects where it needs to be soldered, and give a start button. So when the start button is pressed, the robot starts moving, picks up the PCB and carry on its working. Meanwhile, I'll give you a brief about this GUI. GUI keeps on capturing various information from different sensors. So we have got facial expression sensor, this moving camera, observed camera keeps on recording the facial images in real time. Meanwhile, you can see the soldering thing going on with the collaboration between two robots. So it's a collaboration between robot and a human robot, making it a full collaborative cell.
The robots that you are seeing in our lab, they don't have the cages, and the reason why we don't have the cages, we have tried to understand how we can well manage the safety. So safety is the first and our foremost priority. Robots are repeatable machines. They are very good in repeating the position where we ask them to go, but they are not very good in the accuracy. So we need some extra hand. So we use the metrology devices like this one, the Leica tracker, which use the laser to reflect into the SMR, and we use other devices as well to get this will give you 3D position, and the other devices will give you 6D position as well.
It's largely to do with how people interact with machinery, software, your car, working practices and so on. So what we're interested in doing here is monitoring aspects of physical responses to technology, which might be indicative of how an individual's thoughts, behaviours and attitudes towards it or emotional states can be reflected.
We are also trying to understand how the human is also collaborating with the robot. We are detecting different emotions, we are detecting different facial features, we are trying to compensate any noises or errors that are coming are inevitable because of the sensors information. We are trying to fuse that information and trying to make a meaningful output. We are working very closely with our human factor colleagues who are chartered psychologists, who are giving us hand in order to understand that physiological information as well.
One of the most important factor to know the human emotional state is by its facial expression. It gives the first impression what the human emotion or the expression is looking like.
We need to understand the human physiology. To understand the human physiology, we need to have some senses, and to understand and make the meaningful outcome from the sensors, we need the artificial intelligence, we need the machine learning models in order to make sure we can make some meaningful outcome, and to make sure that the robot can basically understand that outcome.
So far, there has been a lot of implementation around human-robot collaboration in the industries, but in order to achieve same human-robot collaboration, we are still facing significant challenges. When a human and human works together, there's a good coordination and understanding between a human and human, and it increases over the period of time when human knows another human over a period of time. But when it comes to the machines, or as in case of robots here, wherein the human is working alongside the robot, robots can't really understand what the human is trying to say, or what the human emotions are, or what the human intentions are in broader terms.
What we are trying to do is trying to understand how we can flexibly pick up different parts with high variability in them to make sure that we can adapt to those parts, and we don't need specific tooling, and that's the industrial problem that we are trying to resolve. So, and plus what we want because this is a collaborative robot, the green skins, if you are going to touch it, it's going to stop. It is also important, whatever is towards the end of the robot, the end effector that is holding the dinos at the moment, that is also collaborative. So we want to make sure that it is also safe to work along with that. So here we have the flexible gripper under development. So we have two axes here, it's a linear rail, we want it to be as strong as possible, so that's why the machine needs to be strong in order to hold the weight, which is around 15 kilogram and plus. We have these fingers, we want them to be softer to make sure we don't introduce a damage onto the part itself. It needs to go onto the robot, and then we will be able to lift the weight of around 15 kilogram and above, depending on the robot capability.